In this module, we will introduce the concepts of rate law, rate constant, and the reaction order. Let us now consider parameters that influence the rate of a chemical reaction. In equilibrium, a system is defined by its composition, temperature, and pressure. When the system is out of equilibrium, time and the reaction rate come into play. This rate is a dynamic quantity that can change over time and depends on several factors. For homogeneous reactions, the reaction rate is often described by an empirical relationship known as the rate law. This law relates the rate of reaction to temperature, pressure, and the concentration of reactants. Rate law, the function representing the reaction rate, can be expressed as a product of two functions. K, which is influenced by temperature and pressure only, and H, which solely depends on the reactant's concentration. The first quantity K is known as the rate constant of the reaction. The most important property of the rate constant K is that it does not depend on the reactant concentrations. However, it is affected by temperature and pressure. Continuing our discussion of the rate law, we now turn our attention to the concentration-dependent part of the rate law. It can be represented as a product of each reactant's concentration raised to a certain power. Mathematically, it is shown by this equation of the rate law. The power to which the concentration of a reactant is raised in the rate law is the order of the reaction with respect to that reactant. It is typically denoted as N with an index referring to the specific reactant. The reaction order for each reactant signifies how the reaction rate is influenced by the concentration of that reactant. The sum of the reaction orders for all reactants gives us the overall reaction order, typically denoted as N. This overall order provides insight into the sensitivity of the reaction rate to changes in reactant concentrations. A very important aspect that you have to remember is that the reaction orders of a reactant in a given reaction and, by extension, the overall rate law have no relation to stoichiometric coefficients. Every rate law and all reaction orders in it must be determined experimentally with respect to each reactant. Formally, if the reaction rate is not affected by the concentration of a certain substance, its reaction order is zero. All in all, the reaction order of an individual reactant can be integer, zero, negative integer, or even a fractional number. Furthermore, substances formally defined as products of the reaction can also enter the rate law with a corresponding non-zero reaction order. Let us consider the reaction of nitrogen dioxide with molecular oxygen as an example. Its balanced chemical equation is shown here. The experimentally determined rate law expression for this reaction is given by this equation. The reaction rate V is equal to rate constant K multiplied by the concentration of nitrogen dioxide squared and by the concentration of oxygen. According to the definition of the reaction order, this reaction is second order with respect to NO2, first order with respect to O2, and third order overall. Notice that the reaction orders are not equal to the stoichiometric coefficients. In the expression for the rate law, the rate constant K serves as the proportionality constant between the concentrations of the various species and the reaction rate. We have already shown that the reaction rate will always have the dimension of molar concentration over time. Although the coherent SI unit for molar concentration is mole times meter in the power of -3, in practice we typically employ the conventional unit of mole per liter or mole per cubic decimeter, also labeled by an uppercase M. Consequently, the reaction rate is typically quoted in mole per liter per second. Inspection of the equation for the reaction rate demonstrates that the dimension and unit of the rate constant must change depending on the overall order of the reaction to ensure that the reaction rate has the correct dimension and unit. The relationship between the expression for the rate law, reaction order, and the unit of K is presented in the following table. For a zeroth order reaction, the rate of reaction is independent of the concentration of the reactants. The rate law for a zeroth order reaction is given as rate equals K. The rate constant has the same dimension and unit as the reaction rate, concentration per time, and moles per liter per second. In a first-order reaction, the rate is proportional to the concentration of a single reactant. The rate law can be expressed as K times the reactant concentration. Consequently, the rate constant K has the dimension of reciprocal time and the unit of inverse second. Second-order reactions can involve either two molecules of a single reactant or one molecule each of two different reactants. In both cases, the rate constant K has the dimension of inverse concentration times inverse time and the unit of liter per mole per second.